Now that we have the FPGA toolchain installed thanks to Appio, we can start creating our own digital designs using Verilog. In this episode, we'll see how to make basic combinational logic circuits and how they actually get implemented in the lookup tables that are on the FPGA. Let's dive in. For most of this series, we'll be working with the Pmod connector that's at the end of the iCEstick. This just breaks out power, ground, and some input-output pins on either side. This header format was made popular by Digilent for use on their FPGA dev boards, and you can find it on other boards too. The idea is that you can plug in common breakout boards to add features like buttons, LEDs, sensors, and networking. Here is the pinout of that connector on the iCEstick. Pins 6 and 12 are 3.3 volts, 5 and 11 are ground, and the rest are I/O pins directly connected to the FPGA. We'll start off by connecting some buttons to pins 1 through 4 on the right side. Note that these map to physical pins 78, 79, 80, and 81 on the FPGA. We'll only need 3 buttons for this video, but I like to connect 4 just because. Here are the connections. Note that we do not need to add external pull-up resistors on the buttons. We can enable internal pull-up resistors on each of the pins in the FPGA, and I'll show you how to do that. This is the first circuit we're going to make. It's a very basic AND gate. Well, it's an AND gate with 2 NOT gates on each of the inputs. That's because when we press one of the buttons, the line will go from high to low, or from 1 to 0. We want one of the LEDs to light up only when we press both buttons together. Another way to represent this circuit is by using a truth table. Here you can see that when both inputs are 0, the output is 1, which means the LED should turn on. Otherwise, the LED should remain off. As I mentioned in a previous episode, I'm not going to go into the theory behind digital logic, design, and Boolean math. If you are familiar with Boolean algebra, you'll probably know that we can use De Morgan's law to simplify this equation to become the inverse of the output of Pmod 0 or Pmod 1. But we don't actually need to do that. The important thing here is the truth table and that our Verilog code can easily be understood. The first thing we'll want to do is create a folder to hold all of our files, our Verilog file and the physical constraints file. I'm going to go into Documents, Appio, wherever we created the iCEstick folder from last time when we created that example. You should see the example LEDs in here. And then I'm going to create a new folder, and I'm going to call it AND Gate. I'm going to start off by creating my pin constraint folder. So I'm going to create a new blank text document. I'm going to call it AND Gate, just the name of my project again, .pcf. And if your operating system asks, just say yes, it's fine to change the suffix. Note that the next PNR tool will look for the first available .pcf file in a particular folder. So from what I've seen, you probably don't want to have more than one file, as it looks like the first one gets used. I could be wrong on that, but that just seems to be my experience. I'm going to go ahead and open this up with Notepad++. The .pcf file is different from Verilog, so the syntax is not Verilog at all. Comments are the # or hashtag, and I'm going to define my LEDs, so that line is a comment, and I'm going to call set_IO, and I'm going to tab out a few times. You don't need to tab, as long as there's at least one white space, it seems to be read just fine, but you'll notice in Verilog, things like to be tabled out or in tabular form, separated by tabs to create nice columns, which makes things easy to read. So I'm going to do LED 0, and its pin 99 is that LED. So remember that physical pin 99 on the FPGA is connected to LED 0, or in our case D1 on our iCEstick. Then I'm going to define the Pmod I/O pins, and these are connected to my buttons. I'm going to call set I/O again, tab out, and this is where we can define the pull-up. So we do -pull-up for a parameter and just say yes, and that enables the pull-up resistor for this particular pin. I'm going to call this pin Pmod 0, and that's connected to physical pin 78. Let's do the same thing. We'll call pull-up, yes, Pmod 1, and this is physical pin 79. So save that, file save, I already saved it, And now we're going to create our Verilog. So new, let's create a new document. I'm going to rename this the same thing as the project, call it an AND gate, assuming I can spell today. And .v for Verilog. Yes, we can change it. I'm going to open that up in Notepad++ again. Now we're going to create actual Verilog. The C-style comments work very well here, like this works well for line or inline comments, as well as the // comments. I'm going to define my module here and give it a little comment that says when both buttons are pressed, let's turn on the LED. A module is a keyword in Verilog that says I'm going to create a block of functional code. And remember that this is not procedural code necessarily. It doesn't run one line at a time. This is just a block of functionality that gets implemented as hardware when we run synthesis. I'm going to name the module something here. It doesn't have to match the file name, but I'm going to match it anyway. Then we define our interface, the inputs and the outputs that are part of this module. You can put comments in these parentheses, that's fine, and you'll often find that you might have a lot of inputs and outputs for a particular module, so it can help to keep them nicely organized. One way to do that is to do the tabbing instead of spacing, like we saw with the PCF file, to keep columns nice and orderly. As we get to more definitions of inputs and outputs, you'll see that, where you might get buses and vectors and registers, and you can have them on different columns so it becomes readily apparent for whoever is reading your code what a particular input or what a particular output is supposed to be. We're going to name our inputs Pmod 0 and Pmod 1. These should line up with the names that we created in our PCF file. You'll notice that these inputs and outputs are separated by commas. In fact, these could all be on one line. It's very similar to C in that way. You'll see a lot of people's code where they are all on one line next to the module name. As you can see, I'm separating the inputs and outputs by commas, and in fact, you might have them on one line, and in a lot of cases, you'll see them on one line next to the module name, and this is very similar to C in that fashion, where the white space or indentation doesn't really matter here. However, I like to keep them on separate lines because it's easier to read for yourself, maybe later in the future when you're coming back and reading your old code, to easily see what the inputs and outputs are, and they're essentially self-documenting here, but I like to separate them with some comments. Once again, we're going to put the output LED name just like we did in the PCF file, and because that's it, I'm not going to have a comma after that label, and I'm going to close this module out, or the inputs and outputs of this module, this interface rather, with a parentheses and a semicolon. However, that doesn't mean the module is fully defined. We actually define the module underneath it, and we say that it's done with this end module. You can kind of view this as curly braces in C, where this is an open curly brace under here, and this is the definition of the module before the closed curly brace, or in this case where it says end module, that particular keyword. This is going to be a very simple, what we call a continuous assignment in Verilog or HDL. This is not code that's run in the sense that it's executing on a processor. Instead, we're defining hardware. We're saying, basically, create an AND gate that ANDs the lines Pmod 0 and Pmod 1 together after they've been knotted, and connect that to our output line, or in this case, an output pin as it's defined up here and in the PCF file. Because the buttons are active low, we need to use these NOT symbols. When we push button 0 and push button 1, those two pins, those lines, get ANDed together, and the output goes to LED 0. And it's continuous, meaning there's no clocks, there's no execution of code. You can think of it essentially like hardware, like we're wiring something up on a breadboard. Let's save this file, and I'm going to bring up my console. I'm going to make it so that we can read it here. And I'm going to go into my Opio folder, and I'm going to go into iCEstick, and that's where we created our project. So I'm going to go into the AND gate project. And the very first time, before I try to build it, I want to run Opio init, define the board, that is iCEstick. You can see that it creates that .ini file for us that just says, hey, Opio, we're using the iCEstick for our target board. And then I want to call opio build. Hopefully everything works. Don't worry about the no clocks. We're going to be looking into clocks in a later episode, but ignoring that, everything built. So then we say opio upload. And as you can see here, I did not connect my board. Let me connect it. Make sure you have no other FTDI chips connected. That includes things like an Analog Discovery 2 board. With it connected, let's say opio upload again. And when it's done, let's test it to see if it works. If I press either button, nothing happens. It's only when I press both buttons together that the LED lights up. That tells me my design worked. Let's take a moment to talk about what's actually happening in the FPGA. If you look at the ICE40 datasheet, you can find a block diagram that shows what's in a single logic cell. A cell has two main parts, a lookup table, or LUT, and a D flip-flop. We'll examine the D flip-flop later, so let's focus on that lookup table. Notice that it has 4 inputs labeled I0 through I3. Here I've laid out what the entire truth table would look like for our simple AND gate example. We'll assume that Pmod 0 and Pmod 1 were mapped to I0 and I1 for this particular lookup table. Whenever I0 and I1 are 0, the output should be 1. It really doesn't matter what I2 and I3 are, as they're not used. Here is a representation of our 4-input lookup table. Despite what you might initially think, a lookup table is not a collection of logic gates. Instead, it's a simple chunk of memory that has 16 entries, and each entry contains 1 bit. During boot up, the FPGA reads the configuration data from the external flash memory, where it finds information about how to program the random access memory, or RAM, in this particular lookup table. The output section of the truth table is copied to the LUT's memory. The 4 input lines are then used to index into the memory, as the value of the input contains the address of which memory element should be read. This is similar to using a 16:1 multiplexer to select the output from the various memory elements. The output of the lookup table is a single bit, a 0 or a 1. In reality, converting the combinational logic portion of our code into lookup table values during synthesis is where a lot of the magic happens. Let's take a look at a slightly more complex example and introduce vectors. A vector in Verilog is just a way of grouping inputs, outputs, and other named containers together. It's similar to how you might use arrays in other programming languages like C or Python. Rather than assign a name to each input and output, we're going to group them together. A single named net, like what we were using in the previous example, is known as a scalar. Here is the truth table for what we want to accomplish. Notice that we now have multiple outputs. We can write the Boolean equations as follows. We want LEDs 0 and 1 to turn on whenever the Pmod 0 button is pressed, and we want all 3 LEDs to turn on whenever Pmod 0 and 1 are pressed together. Let's implement this in Verilog code. Let's start with the same code that we had last time. We'll go to the .pcf file and let's modify it. The first thing we're going to do to enable these vectors, at least for our inputs and outputs, is define them with these brackets. It's much like you would see for an array in, say, C or Python. I'll continue doing this for each of the LEDs that I want to control, mapping them to a physical pin. So LEDs 0 through 4 are 95 through 99. Just notice that they're kind of in reverse order because that's how the board is laid out. We're going to keep the buttons, but we're going to change them to vector form by using the bracket notation to index 0 and 1. Save the .pcf file, and let's go to our Verilog. Notice here they're not really buttons 1 and 2 anymore, although that's kind of how they're wired. I'll make a note about what I expect the functionality to be, so try that again. The first button lights up 2 LEDs, and if we push the 2 buttons together, buttons 0 and 1, it lights up the third along with those original 2. That is intended behavior. This is where we start getting into columns for our inputs and outputs when we're defining our interface. You can see that this is an input that I'm defining. I'm going to give it the vector name, which is Pmod, and how many bits it is. In this case, we have 2 bits, which are 0 and 1, with most significant bit first, colon, and the least significant bit. I'm going to do the same for the LEDs, which there will be 3 LEDs. You'll notice that we defined 5 here, and that's for you to use later, but I'm only going to use 0, 1, and 2. I expect to see a warning during the build process because 3 and 4 aren't used. It's kind of like defining a variable and not using it. And I want to make sure that my tabs line up. I'm using 4 spaces per tab to make things a little easier, but you'll often find that 2 spaces per tab is perfectly acceptable. In fact, indentation doesn't matter, it's just for you and others being able to read your code. Let's start over with our continuous assignment. You can define something called a wire inside of your module. It's not really a variable, although that's the closest comparison I can make to something like C. It's a net. We're attaching an input to an output or an output to an input on the gates, essentially, even though a lot of things are done through lookup tables. But it's telling the hardware that we want to make connections inside of this module, and a particular connection is not an input or an output. We just need a named net. It helps if you think about it, if you've done any sort of PCB layout and you name some of your nets or wires, it's kind of like that. I realize I didn't talk about this assign keyword. This is essentially making a connection in hardware. We want to say that the Pmod, in this case button, the first button, should be knotted and then connected to this named wire or net. And that is going to always be the case. These curly braces work as a concatenation function in Verilog, but we're not using them for that. You can use them to, say, concatenate 2 buses together, where we have multiple lines or these vectors, and we can put them together to make one larger bus. But here what we're doing is something called replication. We want to say that this not Pmod 0 wire, this net that we've defined as the inverse of our first button line, and we're going to copy that assignment twice, hence the number 2 here, and assign it to LEDs 1 and 0. We're going to assign those 2, which is now replication of not Pmod 0, this wire, to the output pins. Another way to think about this is that we have one output here, and we connect another wire to it, making a T-junction, and it splits out to our 2 pins, LED 0 and LED 1. That's replication in Verilog. This should look similar to our first example, where we are ANDing 2 of the lines together, in this case not Pmod 0, which is a named net, which is the same as just copying this and pasting it down here because it's just a direct connection with no logic, but it does carry this logical NOT gate in front of it. So that wire, the output of that NOT gate, is connected here and then ANDed with not Pmod 1. So this is where we can push both buttons and that third LED lights up. Let's save this. Because this is the same project, I can just call Appio build again without needing to call Appio init. You should expect some warnings here about LED 3 and LED 4 not being used, since we did not use them in the design. Assuming everything builds and synthesizes correctly, let's call Appio upload. If I press the first button, LEDs 0 and 1 turn on. It's only when I press both buttons together that the third LED illuminates with the other 2. I found this reference card from a professor at Imperial College London to be very helpful. I don't know if it lists everything for the 2005 version of Verilog, but it's definitely a good start. Here's your challenge. I want you to implement a full adder in Verilog and run it on your device. The full adder is a very important circuit that performs the basic operation of addition between 2 bits. It plays a crucial role in the arithmetic logic unit, or ALU, that makes up the computational part of a central processing unit, or CPU. This Wikipedia article gives you the truth table as well as the logic diagram for the full adder. I recommend looking at these to figure out how to implement it in Verilog. Note that you might need to invert the inputs if you want to have a button press mean logic high. Here is the full adder working on my iCEstick. When I press any one of the buttons, the output is 1. If I press any 2 of the buttons, the carry out LED lights up. If I press all 3 buttons, the sum and carry out LEDs both light up. So far, we've only looked at continuous assignments, where changes on the outputs are more or less immediately responsive to changes on the inputs, and there may or may not be some combinational logic in the middle. Next time, we'll look at introducing clocks and flip-flops, where we can store and pass data around from one clock cycle to the next. Happy hacking!